SwayamPrabha. Digital India. Educated India.
Let us move on to the next problem. Here, match column A. There are some name of coupling reactions are given. With column B, some reagents are given. So this question was asked in June 2015. So what are all the options that are given? In the column A, the coupling reactions names given are Suzuki coupling, Heck coupling, Sonogashira coupling, and Negishi coupling. And we have some reagents that are used in this reaction. So in the B column, we have the alpha beta unsaturated ester, we have a boronic acid, we have a zinc reagent, we have an alkyne, and we also have a tin reagent. So we have different types of compound that are given, and we have to now match which reaction uses which reagent. So let us look at what is a Suzuki coupling. So Suzuki coupling uses boronic acids or boronic esters, and these are actually coupled with aryl or alkenyl halides to give an sp2 hybridized center. That means it's here what is the example that is given is a formation of the biaryl derivative. We have a boronic acid as the starting material, one of the reagent, and we have the bromo derivative alkenyl here because aryl or alkenyl halide. So we have a bromo derivative that is given here, and these are reacted in the presence of a palladium 0 species. So this is the most crucial one. So in the presence of palladium 0 catalyst, the coupling of a boronic acid with the bromo alkenyl or aryl derivative takes place to give, in this particular case, we end up with a biaryl compound. And here also a stoichiometric amount of a base is used. The base is generally used for the generation of palladium 0 species, and the steps which are involved in the whole process is oxidative addition and transmetallation and finally reductive elimination. So these are all the overall catalytic cycle in many of the organometallic catalyst reactions. And for the regeneration of the palladium 0 species in the catalytic cycle, a base, stoichiometric amount of the base is used in most of the reactions. And this reaction actually received Nobel Prize in 2010. So what is the Heck coupling? The Heck coupling is nothing but, in this particular case, an unsaturated halide or a triflate reacts with an alkene in the presence of a base and a palladium catalyst to give a substituted alkene. So here we have the unsaturated halide or a triflate. So the aryl system is the one which is having the halide unit, and we react this with an alkene. So this is, here we have the alpha beta unsaturated ester that is formed, and here again the palladium 0 species is the catalyst that is involved. And as I told, for the regeneration of the palladium 0 in the whole catalytic cycle, we use a equivalent quantity or one equivalent of a base. And this reaction is again received the Nobel Prize in 2010 because 3 organocatalytic reactions received the Nobel Prize, and we will also see the third one in the next slide. So Suzuki coupling uses boronic acid. So this is one. Heck coupling uses an alkene. So this is the second one. Alkene with the, we also need to see what is the other reactive reagent. So it is not just aryl boronic acid just undergoes any reaction in the presence of palladium catalyst. So we also need a aryl or alkenyl halide. So in other words, most of these systems are actually electron rich systems, and they have a very good leaving group. Many cases we have the chlorine, bromine, iodine, triflate. So these are very good leaving groups. So we do need a good leaving group in one of the substrate for it to undergo the reaction. So if we go to the next one is the Sonogashira coupling. So in the Sonogashira coupling, it is a reaction which involves alkynes. So the terminal alkynes coupled with aryl or vinyl halides in the presence of palladium catalyst, again here this is a +2 state catalyst, and the copper co-catalyst is also involved, copper 1 co-catalyst is also involved in this particular reaction, and an amine base In the previous cases, we only need a base. It's not very specific that you have to use an organic base or inorganic base. But for the Sonogashira coupling, we do need a specific base, that is an amine base is required. And here one alkyne is getting now converted into another alkyne. So mainly this reaction involves a terminal alkyne only. So the terminal alkyne has a hydrogen atom. So this hydrogen atom is now replaced by this particular functional group, that is the Rx. When we talk about that, R group is attached to this particular alkyne. So this is what is the Sonogashira coupling. And the last one is the Negishi coupling. So in this Negishi coupling, we have organic halides or triflides. They undergo reaction with organozinc compounds, then followed by, because they are involved in the carbon-carbon bond formation reaction, here again we use the palladium 0 species, and sometimes nickel also can be used. And in fact, when Negishi first carried out this reaction, he actually used the diisobutyl aluminum hydride as a strong reducing agent in this particular case. But later on, now recently, many people are using without this dibal H in that particular reaction. So this reaction requires either the nickel or the palladium catalyst that can be used. And this Negishi coupling also received the Nobel Prize for in 2010. So this again a carbon-carbon bond formation reaction. So Negishi coupling actually uses zinc. So if you look at the 4 reactions what we have seen so far, Suzuki coupling uses boron reagents. Sonogashira coupling uses copper also is involved or required in this reaction. Negishi coupling requires zinc reagents. So in all the cases we have palladium, but along with palladium there are other things which are essential for this particular reaction to be carried out. So these are all the various coupling reactions which involve organometallic catalyst. So if we go back to our 4 things, so Suzuki coupling uses boronic acid, and Heck coupling requires Sonogashira coupling requires alkyne, Negishi coupling requires the zinc reagent, and Heck reaction requires the alkene. So that way we can easily figure it out what are all the 4 things which are involved in this type of reactions, and we will also be looking at some of the examples in the later part. So this is the next reaction. So here the major product A and B formed in the reaction sequence is, and this question was asked in June 2012. We have an alkyne, terminal alkyne is given, and we have a boronic acid derivative, that is catechol borane is given, and these two react to give reagent intermediate A, and that intermediate reacts with this again is a alkenyl, this is a vinyl iodide that is present here in the presence of palladium catalyst. So these are all the 2 things that are given. And if you look at the reaction A, here we do not have any metal catalyst. So that is one thing you have to keep in mind, because the metal catalyst is used only in the second step. And of course, an alkyne and borane, we have not seen the reaction. Borane reaction we have seen, Suzuki coupling. Alkene reaction we have seen, that is Sonogashira coupling. But they both use metal catalyst, and here there is no metal. So that means this is not a coupling reaction which we are actually had seen earlier. So this is a different type of reaction that we have to keep in mind. So that is the step number 1. And then once we have some reagent, because there is a borane reagent, there is an alkyne. So when alkyne and borane reacts, they may give again another boronate ester may be formed. So that is one thing. So the moment you have a boronate ester, we have a palladium catalyst, we also have a vinyl halide. So that means we are going to look at some type of coupling reaction. So the second step only involves a coupling reaction, what we have seen. The first step does not involve any coupling reaction. So this is the one thing we have to keep in mind before solving this problem. So we have given, there are 4 different options are given. A and B are given for each combinations, 1, 2, 3 and 4. If you look at what are the product that will be formed, see in the A and B there is a cis type addition that had taken place, and in the case of 3 and 4 there is a trans addition of H and B, boron and hydrogen had taken place. So this is the only thing, and when this reaction actually is carried out, we will be seeing which one will be the actual reagent. So in this particular case, it is only the cis addition that is taking place. In other words, 1 or 2 are the only options here for A. So we have to only see between the second one, B. So here we have one type of alkene, here we have another type of alkene. In other words, this is a cis one, this is a trans one. So we have to look at whether it is a cis or the trans product in the second step. So what is the first step? First step is nothing but the hydroboration reaction. So the hydroboration of the alkane takes place. Alkane here, the borane reagent that we use here is the catechol borane. So this undergoes a simple addition reaction. So the attack takes place from the less hindered site. And when the attack takes place from the less hindered site, and this is basically the cis addition. In other words, the hydrogen and boron are added across the double bond from the same site. So that is what is called as the cis stereoselectivity in this particular case. So we end up with this particular borane derivative, and this vinyl boronate derivative undergoes Suzuki coupling, because any boronic acid or boron esters when we are using, that is what is basically the Suzuki coupling, and this undergoes reaction with the substituted vinyl iodide. So that final product what we get is the alkene. So if you look at this is the hydrogen atom here, and this is another hydrogen here, this is another hydrogen here, this is the butyl group here. So the iodine is the leaving group in this particular case. So this reaction actually gives the trans type addition, because iodine and the butane N-butyl group are on the same side, but in the final product the hydrogen and the butane are in the opposite side. So in other words, we get the trans addition here. Let us move on to the next one. So in the following reaction sequence, the structure A and B are respectively. So there is a reaction, we have a alcohol as a starting material. The alcohol reacts with iodine, triphenylphosphine and imidazole to give some intermediate A. That intermediate again reacts with the bromo-chloro-cyano-aryl derivative in the presence of zinc, catalytic palladium catalyst, and catalytic amount of copper iodide to give B. So this is the one which we are going to see, and this question was asked in December 2014. So if you have a hydroxide derivative, we treat with iodine. Obviously what we can think of is iodine, hydroxyl is replaced by iodine. So that means the iodo derivative is formed. So that is the obvious reaction. So here in this option, 1, 2, 3 and 4, only 1 and 2 have the iodo as the required derivative. So in other words, what we can say is the 3 and 4 are not the expected ones. The reason is like the iodination reaction generally replaces a hydroxyl group with the iodine atom. That is a very simple iodination reaction. So in the final product, we have the intermediate has only hydroxyl group. So in 3 and 4, so that means these two are not the options, we can completely ruled out. And now the next thing is like it undergoes some type of coupling reaction. We will not be looking at what is a coupling reaction, just we will keep in mind that it's a coupling reaction. So in other words, we have a iodo derivative in one substrate, we have a chloro-bromo is present in the other substrate. So alkenyl halide is there and we have the iodo derivative that is present. So when the coupling takes place, which one will undergo reaction? Obviously the more reactive bromine will undergo reaction, chlorine will not undergo reaction that effectively. So we can easily figure it out what is going to be the product. The product will be having the chloro group and not the bromo group, because chlorine is less reactive compared to bromine. So in the presence of this metal catalyst coupling reaction, obviously bromine reacts faster. So we can assume, without even looking at how the whole process takes place, without looking at the mechanism, we can easily conclude that one is the our final product, final combination of the reagent intermediate A and B. Let us look at the reaction mechanism to confirm whether it is the right one or not. So the first step is nothing but the simple iodination reaction. So the hydroxyl is converted to the iodo derivative, and in the second step what happens is we have the Negishi coupling. So in the Negishi coupling, we have the iodo, highly reactive iodo species with the catalyst, palladium catalyst is also there. So here we have two halo groups, that is the chlorine is there and bromine is there. As I mentioned in the earlier case, bromine is more reactive than the chlorine. So obviously you can easily figure it out what is going to be the final product. So this is where the chlorine is present in the final product and the bromine is the one that is replaced in this particular reaction. That is a good leaving group. So the bromine leaves compared to chlorine. So let us move on to the next problem. So here the major product formed in the reaction. So we have a allyl acetate type system. So this is nothing but the allylic acetate type system. We have a nitrogen atom that is also present here, and we have the palladium catalyst, triphenylphosphine, triethylamine, acetonitrile, all these reagents are given. So we have a palladium catalyzed reaction, and we have four different options given as the expected product. So if you look at A, B and C, all the thing underwent cyclization reaction. So that is one idea, and the last one we do not have a cyclized product. So most probably this can be a intramolecular reaction because nitrogen is present. Nitrogen is present means it is a nucleophile, so that you can actually figure it out. So once you have a nucleophilic species and you have a metal catalyst that is involved, so obviously some sort of intramolecular reactions are possible in this particular system, and so that is one clue. And the only thing is what we have to see is how it will approach, whether it will approach from the same side or from the opposite side. Because if you look at B and C, the orientation, the stereochemical orientation of the ring junction is the one that is, in one case it is cis, another one it is trans. So that means the nucleophile will come and attack this particular carbon either from the same side or from the opposite side. So that's the only thing we have to figure it out. So in other words, either B or C may be the expected product. So let us look at what are the different steps that are involved in this reaction. So the first step is nothing but oxidative addition reaction, because we are using palladium catalyst in this one. The palladium 0 adds to the allylic acetate. So this is the first step that is happening. So it forms basically the pi complex that is formed. So once the pi complex is formed, what it happens is the next step is the eta 3 complex formation. So that means 1, 2, 3, all the three carbon atoms are now coordinated towards the palladium atom. So in the pi complex, only the pi bond is coordinated towards the metal, that is the palladium. But in the eta 3 complex, 1, 2, 3, all the three carbons, in other words allylic carbon, all the three carbons are coordinated towards the palladium. And in this whole process, the acetyl group also leaves from this particular carbon and gets attached to the palladium center. So because the transition metal has vacant d orbitals, various d orbitals are present. So the lone pair of electron from the oxygen, in this particular case either oxygen or this pi bond, that is the double bond, they also have electrons. So all these electrons can be parked in the d orbitals of the palladium catalyst, palladium metal. So that is the reason this acetyl group leaves and attaches itself with the palladium. So we end up with the eta 3 complex. And in the next step, the intramolecularly, the eta 3 complex actually undergoes a nucleophilic attack because the nitrogen is having a lone pair of electron. So this lone pair of electron can now attack the palladium species. So this is basically the amino group is basically here a hard nucleophile. So there is a major difference. One is like the nucleophile can attack this particular carbon atom, that is one type of attack that is possible, or the nucleophile can actually attack the palladium and then it undergoes the cyclization. So these are two ways the reaction can actually proceed. And since nitrogen is a hard nucleophile, in reaction mechanism, when we are trying to figure it out how the reaction actually takes place, the hard nucleophile will attack only the palladium species. So that is how the intramolecular attack actually takes place, and that leads to the nitrogen from the above phase. And if you look at the methyl group from this one, this is pointing above. Similarly, from the same side, this hard nucleophile will actually attack the palladium and then it will be transferred to this particular carbon atom. So that is how the transfer intramolecularly from the metal to the carbon takes place. So this is how these two are now in the cis orientation or they are below the plane. The hydrogen atoms are below the plane, and this whatever the substituted methylene group and the nitrogen both are on above the plane. So this reaction is called as a Suji-Trost reaction. And last step, basically the reductive elimination is the one which leads to the final product. Let us move on to the next problem. So here the major product formed in the following reaction is, we have a alpha beta unsaturated system. This is treated with lithium and liquid ammonia, followed by reaction with allyl bromide. It leads to an intermediate A, and this intermediate A is now treated with PdCl2 and copper chloride in the presence of oxygen, and in the final step it is treated with ethanolic KOH to give a product B. So these are A and B, and we have 4 options: 1, 2, 3 and 4. So if you look at all the 4 options, the first one is lithium and liquid ammonia. This is nothing but the Birch reduction. So that is step number 1. So the alpha beta unsaturated system undergoes Birch reduction, followed by treatment with allyl bromide. In other words, we are going to do an allylation of this particular intermediate, whatever may be the intermediate. So an allyl group will be introduced. So if you look at 1, 2, 3 and 4, the A all has the allyl group in it. So the only difference is the stereochemistry is the only thing that is different, but all of them has the allyl group in it. So that means all 4 possibilities are possible. So here we cannot rule out anything unless we actually look at how the whole addition takes place. We may not be looking at the stereochemistry in the beginning itself. The next step is, we have a palladium chloride, copper iodide and oxygen combination. So this reaction is nothing but called as a Wacker oxidation reaction. So this Wacker oxidation converts the alkyne, that is the alkenic bond, to a aldehyde or ketone. That is what generally happens. We will have to see whether we will get it. It leads to a carbonyl compound. Let us keep it at that level. So we will end up with a carbonyl compound. We have another carbonyl group here, and we have a carbonyl group here. So when we have 2 carbonyl group, we are going to treat with a ethanolic KOH, that is a strong base. So obviously some reaction similar to an aldol type condensation or something are expected here. So in other words, that will lead to a cyclized product most probably. So this is one clue. We get another, this is the second clue we have in this reaction. So all possibilities 1, 2, 3, 4 for A is possible, but for B we have to now very carefully look at what are actually possible, what are not possible. And if you look at B, all are again cyclized product. So we are not so sure which is going to be the product. So in other words, the guessing is not possible in this particular reaction, because this question is asked very nicely. So you cannot easily guess and figure it out what is the expected product here. This question was asked in June 2015. So now we have to move into how to find out what is the product that is formed. So this alpha beta unsaturated ketone undergoes Birch reduction. So the first step is the formation of the enolate anion, because lithium transfers 1 electron. This is nothing but a single electron transfer process, and it ends up with a radical anion, that is the enolate anion. And in the second step, the solvent gives that hydrogen atom to that enolate oxide anion. So we end up with a enol derivative, that is the radical enol is actually formed. In the second step, another lithium transfers 1 more electron. So 2 single electron transfers takes place. Here we end up with the carbanion. So this carbanion can actually be tautomerized. Oxygen is more electronegative than the carbon. So this can easily tautomerize, where the negative charge on the oxygen is possible, happening. So we end up with a enolate anion. So once you have an enolate anion, what can happen is this carbon can also become like a negative charge, because in the charge reversal this will polarize like this towards. So in other words, this carbon is the one where the allylation will take place. So we have a good leaving group. So we have the anion here. So the anion will attack this carbon with the concomitant removal of the bromide. So in other words, we end up with a allylation. So now how the allylation will take place? Because of the presence of a methyl group, that if it is present or projected above the plane, that plane is hindered for the attack of this particular reaction, because bromine is a very big atom. So the attack has to take place from the bottom side, and we end up with a trans stereochemistry between these two carbon atoms. And in the next step, the allyl group undergoes Wacker oxidation. So the number of steps are given here. So the Wacker oxidation leads to the multiple steps are there, because we have seen Wacker oxidation earlier also. This involves beta hydride elimination, tautomerization, and that tautomerization, because we end up with an enol. So here the hydride, the beta hydride elimination leads to the ene formation. Terminal ene is formed, and this undergoes tautomerization to give the carbonyl group, that is the ketone is formed. So we have the diketone that is formed in this particular reaction. So once the diketone is there, we have a acidic hydrogen atom, and we are using a strong base. Ethanolic base is there. So this will abstract this hydrogen atom to give a anion on this carbon, and this can actually exist as a enolate, and this is a more stable species, so that is easily formed. And this anion will now attack this electrophilic carbon atom with the concomitant formation of the hydroxide derivative, because the reaction happens in the aqueous condition. So the enolate, the oxide anion which is formed finally will abstract a hydrogen atom from the solvent, and it will form the hydroxide derivative. Still we have a base in this reaction. So the base will abstract another hydrogen atom. So we have two hydrogen atoms, one here and one here. So these two hydrogen atoms are adjacent to the hydroxy group. So whichever hydrogen is removed, that will lead to the formation of an alkene. The double bond will be formed there. So in this top case, where we have a alpha beta unsaturated system that will be formed after the elimination of the water molecule, and here we do not have a alpha beta unsaturated system that is formed. So in other words, the elimination takes place to give the more stable alpha beta unsaturated derivative. So let us move on to the next problem. So the major product formed in this particular reaction is, of course, this is a pretty lengthy reaction. We are going to look at there are, if you look very carefully, A, B, that means every step has at least multiple reagents. In other words, this is a pretty lengthy reaction. We are going to look at how the entire process leads to the expected final product. So that is the question that is asked. This is asked in June 2015. So there are various combinations. A, 1, 2, 3, 4 are given. In the first step, we have a strong base. Sodium methoxide is a strong base. Methyl iodide is used, and the sodium chloride and the wet DMSO is used in the second step at a high temperature. And in the second set of reaction, LDA at minus 78 degrees centigrade and TMSCl is used. And in the last step, we have tertiary butyl chloride and the TiCl4 at 50 degree. So these are all the various reagents that are given. And if you look at most of the reactions are same, except in the one of the cases we have sodium hydroxide and HCl, that is also given as one of the reagent. Triethylamine TMS chloride at room temperature is given. Morpholin and acidic conditions are given. So there are various reagents which are given. Let us look at what are each reagent will do. Based on that, we will have to figure it out how the reaction will actually proceed. Sodium methoxide and methyl iodide. So this is nothing but a strong base used for methylation reaction. So the strong base abstracts a proton, and the methylation happens with the methyl iodide. So this is one type of reaction. Another one is sodium chloride wet DMSO under 160 degree. So this is basically the decarboxylation of beta ketoesters after hydrolysis, because the wet DMSO will hydrolyze in the presence of sodium chloride, and once you hydrolyze, when you get a beta keto acid at high temperature, that undergoes decarboxylation. So this is the second set of reaction. And LDA minus 78 and TMSCl is generally used for the protection of the hydroxyl group by the TMS ether, that is silyl enol ether is formed. So for that purpose, we need the LDA TMS conditions. If LDA is not used, we can also use other milder bases that will only protect the hydroxyl group as a TMS ether. But when we use LDA, then we will end up with the enol silyl ether rather than simple silyl ether. So this is a little bit tricky thing you have to remember, otherwise you will miss out in choosing the right reagent for this particular reaction. And the next one is tertiary butyl chloride and TiCl4. This is generally used for the, see, the TiCl4 is nothing but a Lewis acid, like an aluminum chloride. Okay, let us assume it is very similar to a Friedel-Crafts reaction. So you have a tertiary butyl halide which can easily give a carbocation, and you have a Lewis acid. So in other words, we are looking at something similar to a Lewis acid based reaction. So TiCl4 is mainly used as a Lewis acid in this particular case. And we have sodium hydroxide and HCl. So this combination, sodium hydroxide and HCl, that means in the next step only we are using HCl. We are not mixing sodium hydroxide and HCl in the same part. Okay, so aqueous HCl, sodium hydroxide will facilitate hydrolysis, and if it is present as a carboxylate anion or an alkoxide anion, the HCl will give the proton to make it the neutral species. So that is the reason always a base hydrolysis is followed by acidic workup. And the next one is the triethylamine TMSCl. So this will mainly use for the formation of silyl ether, not silyl enol ether. And we have sodium hydride and tertiary butyl chloride. Sodium hydride is a strong base, so it will be used for the alkylation reaction. Morpholine and H+, this is generally used for the enamine formation. Methyl iodide and water is generally used for the alkylation followed by hydrolysis. So these are all the different reagents that are used. And let us look at this one, because this is a very lengthy process, so I will go very quickly in this one. So the first step is there is a, this particular carbon is having the most acidic proton. This is nothing but the beta keto ester. So this methylenic hydrogen is the most, here methanic hydrogen is the most acidic one. The strong base abstracts this proton, we end up with the anion, and this anion can exist as a enolate anion. So because of it can exist as an enolate anion, this is formed very quickly, and this enolate anion attacks the methyl iodide. In other words, we actually carry out the methylation reaction simply. Okay, once the methylation is over, then what is the next step? So we use sodium methoxide or any strong base with methyl iodide to give the methylation. That is step number 1. Then what is step number 2? The step number 2 is used, we are going to use some hydrolysis conditions, and this is a beta keto acid. Once if it is hydrolyzed, we end up with a carboxylate anion, and the carboxylate anion can very readily undergo decarboxylation, because beta keto acids can very readily lose carbon dioxide, because the driving force is the formation of the gaseous carbon dioxide for this decarboxylation reaction. So that will end up with the methylation that is occurring in this particular reaction. So the ester group which is present in the starting material is hydrolyzed and eliminated to give the simple alkylation reaction. So this is first one. And once the alkylation takes place, then we are going to protect this particular enol with the enol silyl ether, and then we will take it further to the last step, that is the Lewis acid catalyzed reaction. So if you look at very carefully, the first one is the methylation of the beta keto ester that is happening here, and the second step, the sodium chloride and the wet DMSO hydrolyzes this into a carboxylate anion, and under high temperature this loses carbon dioxide molecule. So in other words, we end up with the loss of CO2, and the simple methylation actually takes place. And once here we have a oxide anion. So this oxide anion can actually abstract a hydrogen atom from the solvent, and we end up with a simple carbonyl derivative. So in other words, we have just methylated the starting beta keto ester. That's it. So once the methylation is over, the next step is the treatment with LDA. So the LDA abstracts the acidic hydrogen, and we end up with the enol. Enolate is formed under low temperature, and this enolate reacts with the trimethyl silyl chloride to give the enol silyl ether. So once the enol silyl ether is formed, the treatment with the tertiary butyl chloride with the TiCl4 produces the tertiary butyl carbocation, and this is nothing but the Lewis acid. So this now undergoes the tertiary butyl insertion on this particular carbon atom. So these are all the various steps involved. So in other words, what are the 4 reagents that will be used in the overall process is, we have to use the methylation of beta ketone ester with a strong base and methyl iodide. Then wet sodium hydroxide, sodium chloride and DMSO facilitates the decarboxylation. Then LDA used for the formation of the enol silyl ether, and in the last step alkylation, tertiary butylation of this particular species, intermediate takes place. So these are all the 4 reagents that are used in this reaction. And let us move on to the next one. So here the major product formed in the following reaction is, we have 2 palladium catalyzed reagents that are used in this one. This question was asked in June 2015. We have a bromo, we have the iodo in the starting material. So this is nothing but the indole derivative having 2 different substituents, and we have 2. If you look at the catalyst is same palladium acetate in the presence of triphenyl phosphine and triethylamine. That same palladium 0 reagent catalyst will be formed in both the cases, and in one case we have the alkene, and in another case also we have the alkene. So in other words, reaction looks very simple. The only difference is we have an iodine and bromine. So in other words, we can clearly identify iodine is more reactive compared to bromine. So we can easily figure it out what are the products that are going to be. The first step, the iodine will undergo reaction here, and in the second step bromine will undergo the reaction. So if we can figure it out what is the right product, we have the right answer for this one. So it is very simple, straightforward reaction. So here we can easily guess, or even without looking at the mechanism we can say. Let us look at how the reaction actually proceeds. So in the first step, this is nothing but the palladium catalyzed Heck reaction. So here the iodine is replaced, so this particular group is added here, that in the first step, and in the second step again this is the good leaving group that undergoes reaction in the next step. So iodo reacts better than bromo is the only thing we have to look at in this reaction, and with that we can easily figure it out what is the final product that will be obtained. So this is another important reaction. So here the major product formed in the following reactions. Actually 2 similar reactions are asked in 2 examinations. One is December 2015 and another one June 2017. Both of them have more or less the similar substrate. So we have the iodo and the cyano in the 2015. Instead of cyano we have the methyl group in the 2017. So if you look at the reaction, they all are looking very similar to the same type. In the 2015 they had given the final product, but in 2017 they had given 2, that is one intermediate what that will be formed, they also asked that, and what is going to be the final product. So these are all the 2 things included in the 2017, and the reaction follows exactly the same. So I will take only the top one, and we can easily work out the same for the second one also. So this starting material has 2 groups. One is the allyl nitrile. So this group is the allylic nitrile that is present, and the second one is the vinylic iodide. So these are all the 2 different reactive species that are present, and we have to now figure it out which one will undergo reaction quickly. Based on that we are going to decide what product that will be formed. So both uses a palladium Heck reaction, that is a palladium catalyzed Heck reaction. Triphenyl phosphine and palladium acetate is used. So the initial step is the oxidative addition reaction, because this palladium actually adds to the double bond, and then the next step is the carbometallation reaction. So if you look at the reactivity, the vinyl systems are more reactive compared to the allyl systems. So that is the only thing you have to keep in mind, because if the allyl system undergoes reaction we will end up with a different type of product. So here the vinyl system undergoes the reaction first, and then the allyl reaction, the allyl group undergoes the reaction. So the first carbometallation or the oxidative addition happens on the vinylic iodide, because iodide is a very good leaving group. So that is one of the reason that reaction happens on the vinylic iodide system. So then we have that palladium iodide that is formed, and this undergoes the carbometallation reaction. In other words, the cyclization actually takes place, and we end up with the cyclic bicyclic system that is formed. And once the bicyclic system is formed, we already know the next step is the beta hydride elimination. So the beta hydride elimination leads to the formation of the double bond here. So this is how the whole process actually takes place. And if the cyanide is not there in its place, it is the methyl group that is present here. So that way we can easily figure it out how the reaction actually proceeds. And let us move on to the next product. So here the major product formed in the following reaction is, there is an aldehyde is given, we have a dibromo derivative, alkene dibromo derivative is given. These are reacting in the presence of zinc to give some intermediate A. So if you look at 1, 2, 3, 4, the intermediate A, or the first one, is nothing but the bromine is included, hydroxyl is included. In other words, a simple condensation reaction. That is what we can look from the initial analysis. So they all look more or less similar. So that means this may be one of the all possibilities are there for this particular reaction. So we cannot rule out anything now. We have to now look at the second one. In the second one, what is the reagents which are used? TBDMSCl, pyridine and DMAP. So this is mainly used for the hydroxy protection. So that means we get a hydroxyl in the first intermediate. That hydroxyl group of the intermediate is protected as the TBDMS chloride, TBDMS group, tetrabutyl dimethyl silyl group. And in the second step, we are actually doing a Heck reaction, or palladium catalyzed reaction. So this is the one thing we have to actually look at. That means some intramolecular reaction is going to take place because we do not have another separate substrate. So there will be one place which is going to undergo intramolecular reaction we have to look for. So how the reaction actually proceeds is, basically we have an aldehydic group, and the zinc actually adds to the allylic position of the bromide derivative. So this is the first step that actually happens. So since we have two bromine atoms, but the reaction actually occurs only on the allylic bromine and not on the vinylic bromine. So here the highly reactive bromide, that is the allylic bromide, undergoes reaction to give allylic zinc bromide. So this is a crucial thing we have to remember. In the previous case, for the vinylic iodide underwent reaction compared to allylic acetate or cyanide. So we have to be very careful in each reaction how each reactions under the reaction conditions differ in reactivity. So here the next step is, once the zinc is added, it is simply undergoing this allylic zinc bromide undergoes reaction with the aldehyde. And here the most crucial thing is the allylic rearrangement that is taking place. Here we have a 6-membered ring that is formed in this reaction. This is very, very crucial for this reaction to take place. And this 6-membered cyclic transition state leads to the product as shown here. So the carbonyl, that is the aldehydic group, becomes a hydroxy group here, and the allyl group is actually added. So how the allylic group is added? The allylic bromide is the one which is actually connected here. So that gets converted to the terminal alkyne. So in the starting material, if you look at very carefully, this allylic carbon has the bromo substituent, and this one is now converted to the alkene. So basically a allylic rearrangement actually takes place. So this is what we have to remember very carefully, because if you are going to use, in this particular system we have unsubstituted carbons. So this carbon is unsubstituted, this has only the bromine. So here again we can say there is no methyl group. But if, say for example, there is a methyl group here, then while writing the product we will have a difficulty in identifying where that methyl group will go. So unless we know about this particular allylic rearrangement, it will be very difficult to predict what type of the product we are going to get. So here the allylic bromine is the one which is getting converted to the alkene here. And the other bonds, we know how they are actually formed. The bond is formed between the terminal carbon and the carbonyl carbon. So that is how the reaction gives this particular bond. This CC bond is formed between the alkenic carbon and the aldehydic carbon. So this allylic rearrangement leads to this particular derivative, and we have a hydroxy group. Then this hydroxy group can be protected with the TBDMSCl and pyridine and DMAP. So this is protected. And we have the vinylic bromine, we have the alkene. So when you have vinylic bromine and alkene, you know what is the reaction you can actually carry out in the presence of palladium. So this particular thing undergoes cyclization to give the final product as shown here.